Hello! In this video, we're going to prove the following theorem. Suppose G is a group and A is an element of G with order n. Then for all integers k, the group generated by a to the power of k is equal to the group generated by a to the power of GCD of n and k, and the order of a to the power of k is equal to n over the GCD of n and k. Now, given any group element G, to say that the order of G is equal to n means the following. It means that n is the smallest positive integer such that G to the power of n is equal to the identity element. If there is no such positive integer n such that G to the power of n is equal to e, then we say G has infinite order. And also, the group generated by G is the set of all elements of the form G to the power of m, where m is an integer. And we have proven for any group element G, the order of G is equal to the order of the group generated by G. Now, in proving this theorem, we're going to be using a fact about the GCD, which is as follows. Suppose a and b are integers that are not both 0. Then there exist integers s and t such that the GCD of a and b is equal to as plus bt. Okay, so now let's get into proving this theorem. To start out the proof, since we're trying to prove a statement about all integers, let's give ourselves an arbitrary integer. I'll call it k. From here, the whole goal is to show that these two statements are true. Now, we're going to say that the identity element of our group is E. And for convenience, we're going to write the GCD of n and k as D. Now, we know that D is a divisor of both n and k. In particular, since D is a divisor of k, this means that k is equal to D times some integer. I'll call it integer r. Also, according to this result, we know that there exist integers s and t such that D is equal to ns plus kt. Okay, now let's first show that these two guys are equal. Now let's show that these two groups are equal. We're going to show that the group generated by a to the power of k is a subset of the group generated by a to the power of d, and we're going to show that the group generated by a to the power of d is a subset of the group generated by a to the power of k. Now, to show those two inclusions, it suffices to show the following. If we can show that a to the power of k is an element of the group generated by a to the power of d, then that implies the entirety of the group generated by a to the power of k belongs to the group generated by a to the power of d, and vice versa. Okay, so let's first show that a to the k belongs to the group generated by a to the power of d. Now, since k is equal to d times r, a to the power of k is equal to a to the power of dr, and by properties of exponents, we can rewrite this as a to the power of d to the power of r, but this is a to the power of d to the power of some integer. So this guy must be an element of the group generated by a to the power of d. So this shows that a to the power of k belongs to the group generated by a to the power of d. So we can conclude that the entirety of the group generated by a to the power of k must belong to the group generated by a to the power of d. So now, let's show that a to the power of d belongs to the group generated by a to the power of k. Now, we know that d is equal to ns plus kt. So this is a to the power of ns plus kt. But then by properties of exponents, we can rewrite this as a to the power of ns times a to the power of kt. By properties of exponents again, a to the power of ns is just a to the power of n to the power of s. A to the power of kt is just a to the power of k to the power of t. But since the order of a is equal to n, we know that a to the power of n is equal to the identity element. So we can replace a to the power of n with the identity element, but we know that the identity element to the power of any integer is also the identity element. So this is just the identity, so we have the identity times a to the power of k to the power of t, so then this is just going to be a to the power of k to the power of t. But this is a to the power of k to the power of some integer, so this guy must be an element of the group generated by a to the power of k. So this shows that a to the power of d belongs to the group generated by a to the power of k. So we can conclude that the entirety of the group generated by a to the power of d belongs to the group generated by a to the power of k. And so, with these two inclusions, we can conclude that these two groups are equal. So that verifies the first result. Now let's verify this result. And we want to prove the order of a to the power of k is equal to n over the GCD of n and k. And actually, since we know that these two groups are equal, their orders must be equal. But according to this result, we know that the order of the group generated by a to the power of d is equal to the order of a to the power of d. And the order of the group generated by a to the power of k is equal to the order of a to the power of k. So if we want to show that the order of a to the power of k is equal to n over d, that suffices to show that the order of a to the power of d is equal to n over d. So we're going to show that the order of a to the power of d is equal to n over d. And how do we show that the order of a to the power of d is equal to n over d? Well, according to the definition of order of an element, we want to show that n over d is the smallest positive integer, such that a to the power of d to the power of n over d yields the identity element. In other words, we want to show a to the power of d to the power of n over d is equal to the identity element, and then we want to prove if gamma is any positive integer that satisfies that same condition, then n over d is less than or equal to gamma. So n over d will be the smallest positive integer that satisfies this condition. So let's first show that a to the power of d to the power of n over d is equal to the identity. Now from properties of exponents, we can just multiply d and n over d. So this is a to the power of d times n over d. And we know that d times n over d just gives us n. So this is a to the power of n. But since the order of a is equal to n, we know that a to the power of n is equal to the identity. So this shows that a to the power of d to the power of n over d is the identity. But now we want to prove that n over d is the smallest positive integer that satisfies this property. To do that, let's give ourselves an arbitrary positive integer, gamma, such that a to the power of d to the power of gamma is equal to the identity. Well then, we can multiply the exponents, so this is just a to the power of d times gamma. So we have a to the power of the positive integer d times gamma is equal to the identity. But since the order of a is equal to n, this means that n is the smallest positive integer that's able to do this. So n must be less than or equal to d times gamma. And then, dividing d to the other side, we get n over d is less than or equal to gamma. And that shows n over d is the smallest positive integer that does this. So, the order of a to the power of d must be equal to n over d. But if you recall, this is sufficient to show that the order of a to the power of k is equal to n over d, because we know that the order of a to the power of k is equal to the order of the group generated by a to the power of k, but the group generated by a to the power of k is equal to the group generated by a to the power of d. So their orders must be equal, but again, the order of the group generated by a to the power of d is equal to the order of a to the power of d. And the order of a to the power of d is equal to n over d. So this shows that the order of a to the power of k is equal to n over d, which is exactly what we wanted. So we have proven both of these things, so we're done. This completes the proof. And so yeah, that's pretty much it for this video.